Hello, my name is Michael Collins. This is a pre-recorded presentation for the 2021 International Conference on Cognitive Modeling, titled Parameter Correlations in the Predictive Performance Equation, Implications and Solutions. Mathematical models of learning and retention offer several benefits. We can better formalize our theories, we can quantify our theories using various statistical methods, and we can implement them into technologies. Mathematical models of learning and retention can also be used in kind of one or two different ways. So we can use them to predict future performance, or we can estimate latent psychological constructs such as learning or decay rates. One specific model of learning and retention that I'm going to talk about throughout this presentation is the predictive performance equation. It's been shown to account for behavior across a variety of different tasks, both laboratory and real world. However, if models are going to be used to estimate latent psychological constructs from their free parameters, certain formulations of models equations can obscure these interpretations. These are nested equations or muddled units. Here we see the predictive performance equation. It's composed of 5 separate equations with 4 fixed parameters: learning rate, lag between trials, number of exposures on a task, and time between exposures. 4 free parameters: decay intercept, slope, threshold, and representing prior knowledge. And it represents 3 psychological aspects of learning. So 1, the power law of learning, power law of decay, and the spacing effect. Although the PP is accounted for human behavior in a variety of different scenarios, there are 2 aspects of the PP's structure that can obscure the interpretation that can be made about the model's best fitting parameter estimates. This is 1, muddled units, seen here in equation 5, with activation being a function of n, which is instances, and t, which is a function of weighted time. The second is nesting equations into each other. This is seen here with activation being nested within the logistic term of equation 6. In order to fix these 2 aspects in the PP, we created the modified PP, which addresses these 2 problems, making 3 changes to the PP's overall structure. So the first, we modified the decay term, giving the model a learning rate and a decay rate, which affects the spacing term. And second, we modified both the learning term and the forgetting term so that they're unitless metrics. And third, we removed the logistics term, allowing performance to be a function of both the learning and decay term directly. Given these 2 versions of the PP, we conducted a model comparison. Our data set consisted of 61 individuals in a paired associate studies. Both the standard and modified PP were implemented as Bayesian hierarchical models. And with our model comparison, we asked 3 questions. 1, how well could each model account for the participants' performance across various learning schedules? What was the correlation between each model's free parameters? And 3, what was the correlation between the model's free parameters and certain aspects of the participants' performance? Here we see both models fit to the human data across the 6 individual learning conditions. We see that both models fit the data fairly well. However, a Bayes factor found that the modified PP was highly favored compared to the standard PP when accounting for performance in this experiment. Looking at the correlation across each of the model's free parameters, moderate correlations were observed between the free parameters of the standard PP, shown here on the top figure. However, little correlation was seen in the 2 remaining parameters in the modified PP, seen here in the bottom figure. Finally, we examined the relationship between each model's free parameters in 2 aspects of the participants' performance: their overall performance, shown in the top row, and the retention between sessions, shown here in the bottom row. In the standard PP, the tau is the largest correlation with both aspects of performance, as well as the B and M parameter having moderate correlations. This again shows that multiple parameters are accounting for similar aspects of performance in the standard PPE. However, in the modified PPE, while in the modified PPE, both the B and M parameters correlate with both aspects of performance, but the B parameter shows a higher correlation with retention between sessions, and the M parameter shows a higher correlation with the overall participants' overall accuracy. So for this brief presentation, we evaluated the structure of the predictive performance equation, and we identified 2 aspects of the PP's structure that lead to intercorrelation across the parameters, which obscures the interpretation of what these parameters mean in the context of a learning theory. So we reformulated the PP to make the modified PP to decrease correlation between parameters. And our results showed that the modified PP improved the parsimony compared to the standard PP. We decreased intercorrelation between the modified PP's remaining parameters, and the modified PP's parameters highly correlated with the specific aspects of the participant's behavior. Thank you for coming to listen to my brief presentation. If any of you have any further questions, I would suggest you go look at the paper where more details can be found, and I look forward to interacting with many of you during the poster session.